Evaluating a Kubernetes environment involves testing the communication between a web application and its persistent data source across the cluster's internal network. By following this build, you will deploy a fully operational application that communicates with a Postgres database, entirely managed within a Kubernetes cluster. You will need 4 tools to follow along: Docker for building images, a local cluster like Minikube, a code editor, and a Docker Hub account to host your container registry. Establishing this local environment early prevents configuration errors from stalling your deployment later, allowing the focus to remain on the architecture itself. We begin with the application tier, using Python and the Flask framework to create a simple web API that handles incoming traffic. To maintain flexibility, the script uses environment variables for database connection details. This allows Kubernetes to inject the database hostname and credentials at runtime without modifying the source code. Since Kubernetes only orchestrates containers, we must package the Python code and its library dependencies into a portable Docker image. For the web server, we use gUnicorn. Unlike basic development servers, gUnicorn uses multiple worker processes to manage concurrent requests, providing the stability required for a cluster environment. Standard container builds often run as the root user by default. This creates a security risk. If the application is compromised, the attacker inherits full administrative privileges within the container. We resolve this by creating a dedicated system user within the Docker file. By explicitly switching to this non-root user before the application starts, we ensure the process runs with the minimum permissions necessary. Hardening the image with restricted user permissions ensures that even if the application process is breached, the attacker is confined to a low-privilege environment with limited access to the container's file system. With the Docker file finalized, use the terminal to build your image, tagging it with a version number for easy tracking. Next, push the image to your Docker Hub registry. This makes the image accessible to Kubernetes, regardless of where your cluster nodes are running. Warning tone: ensure you replace the placeholder username in the build command with your actual Docker Hub ID. If the registry path is incorrect, the cluster will be unable to pull your image. Now we define the infrastructure. We use a single YAML manifest to declare the desired state for both the application and the database. We isolate the app and database in separate pods, letting us scale the web tier safely during high traffic. To bridge them, we use Kubernetes services. These stable internal addresses ensure the app consistently finds the database, even if the database pod restarts. This 2-tier architecture allows you to update or scale the application logic independently of the data storage layer. To launch the architecture, apply your YAML manifest using Kubernetes. This sends your configuration to the Kubernetes API server for execution. Use Kubernetes get pods to monitor the startup. You are looking for all components to reach a running status, indicating the images were successfully pulled and the container started. If you are working locally in Minikube, use the service command to open a network tunnel, which exposes the web application to your browser. If the application pod restarts initially, do not be alarmed. Kubernetes automatically cycles the pod until the database is fully initialized and ready to accept connections. Once all pods are stable, the system has successfully applied your resource limits and established the secure network path between your tiers. Refreshing your browser confirms the success of the build. Each visit triggers the API to record a new timestamp in the Postgres database and display the results on screen. You have successfully containerized a Python API with non-root security and orchestrated a multi-tier deployment using Kubernetes services. While the architecture is functional, one security gap remains. The database password is currently stored as plain text within our YAML file. To reach true production-grade readiness, the next step is to replace these hard-coded values with Kubernetes secrets and implement persistent volumes to ensure your data survives beyond the life of a single pod.